Now, this lecture is in a way you can say an introduction to what is called as a CAD CAM, which is an integrated view of design and manufacturing. Okay. Now, CAD CAM can be defined as for example, computers to assist design and manufacturing activities when they are performed in an integrated manner and are not as islands of automation. What we did in our earlier lectures is more like a islands of automation, okay. A computer based automation of a design process and computer based automation of some of the manufacturing activities more in a separate way, but now we are looking more in an integrated manner. And it is also true that benefits of CAD CAM would be much more when you do it in a much integrated manner. Okay. There are like organizations who use computers only for design process, then there are also organizations who use only for manufacturing processes, then there are organizations who use them separately, then you also have a class of organizations who actually look it from more from the integrated point of view. So, by the word CAD CAM one usually refers to this particular thing. But if you really look at the definition which is given for CAD CAM, particularly from various books which are published, you may come across various definitions and domains. The reason is the subject has evolved over like 40 years, and the definition is also continuously changing. For example, a book which is written something like about 20-25 years back, there were certain CAD CAM technologies, but if you really look at now, there is a more integrated approach compared to what it used to be a few decades back. So, I put that CAD CAM is something which is greater than CAD plus CAM. Okay, that is what is the basic summary of the definition. Now, this particular picture should give in a way an integrated framework for computer aided design and manufacturing. If you look at for example, what we discussed earlier is in our first lecture that computers can be used for the design process, they can be used at a conceptual design process and more so in a design detailing, okay, or analysis or configuration kind of a design, and also in terms of carrying out analysis like finite element analysis, they can be applied for analysis like kinematic and dynamic analysis. So, one can think of let us say using a CAD tools in this particular domain and restrict to only use of computers to this domain and call it as a CAD, that is very valid definition. And in the second lecture we looked at particularly use of computers for manufacturing like CNC program generation or computer aided inspection. We also looked at computer aided assembly. So, this can be considered as more of a computer aided manufacturing. Now, what is shown here is only a set of activities. Okay. This is not complete design and manufacturing activity. Design and manufacturing activity overall involves many other activities which are not shown here. So, this is just a representative slide. Now, these activities which we call as a computer aided design and then computer aided manufacturing, they are all related with, they can be related using let us say a concept of geometric modeling. So, this is called as a geometric modeling based integration of design and manufacturing. Now, what is really happening in a typical product design and manufacturing process is somebody may start with a design, okay, go for analysis tools, may come up with optimization and finally arrive at let us say a design detailing. During a design process, the geometry continuously evolves. Okay. So, you start with nothing, and at the end of a design when you say that I have completed my design and I have documented, that means your one of the aspects of your design information is geometry, in fact key information is geometry. So, the geometric model continuously evolves as a part of a design process. You may have seen people who are using computer aided design tools. For example, a designer sits in front of a computer, then start with the design process and starts with let us say adding a few features, okay, like start with a simple you can say start with a simple geometry and continuously modify this particular geometry as a part of the design process. And during this particular process you have to check for certain functional requirements, you have to check whether the design geometry will do the intended function satisfactorily or not. So, for those situations you use analysis tools, and based on the feedback from the analysis you modify your design. Okay. And this is a, you can say, an iterative process. It is like you cannot say that design is a sequential process. You start with a step 1 and end with a step 7 or step 8 where there are no iterations. It is a iterative process, and that is what is usually done in this. Now, the geometry evolves as a part of design. Now, the same geometry is required at various stages of manufacturing. For example, if I want to, suppose if I have a component which has to be manufactured on a CNC machine, let us say it may be a CNC machining center, or it may be a CNC punch press, or it may be a CNC arc welding machine. Now, one of the inputs to generate the CNC program is geometry. After all, what is manufacturing? Manufacturing is like one of the ways of looking at is realizing the design geometry through various manufacturing processes. So, since you are realizing the same geometry which has been designed by the designer, so geometry forms one of the key inputs in any manufacturing. We also looked at computer aided inspection in our last lecture. So, one way of, or the major objective of any inspection process is to see that the manufactured geometry meets the design geometry within certain tolerances. Okay. That means there is not much deviation in the two. So, you are again using the geometry which has been designed, you are getting a geometry which comes from the manufacturing. Like after a component is manufactured, I can measure it on a CMM and model the manufactured geometry, and then compare with the design geometry which is available and see whether the part meets the, you can say, quality requirements or not. So, again geometry is an input, and in assembly also we know that you make use of the geometric features of various parts to carry out the assembly process or even to automate the assembly process. When you say that there are two parts which are mating and they have a mating relationship, so this relationship is usually expressed in terms of some geometry. For example, you say that a solid shaft mates with a hollow shaft, you basically make use of the outer cylindrical surface of a solid shaft and inner cylindrical surface of a hollow shaft and say that these are the two mating surfaces. So, again you are making use of a geometry which is a part of which comes as a part of a design, and so what we really look at here is this is geometry evolves as a part of a design process and it is used by a manufacturing process. Now, if this is true, then one should really, like I have put the arrows how the geometry is basically modified or input from various activities. You see that the arrow has two directions. It is not necessary that design only gives a geometry and there is no modification. It goes through modification. Like when I carry out a finite element analysis, I give a input geometry, carry out the analysis, and I see that either it does not meet the strength requirements, then I can go and change its geometry, like change the section so that now it has a better strength kind of a thing. So, geometry is modified as a part of process. It is true that in a manufacturing activities also there is a feedback which is sent to geometric model for basically changing the geometry. Like I carry out, let us say we discussed about what is called as a design for manufacture and design for assembly. So, in DFM and DFA, what one is trying to do is that carry out the manufacturing operation either in real world or a virtual world, then based on the feedback you are actually trying to modify the geometry or suggesting some changes so that a component can be manufactured in a more optimum manner. So, all the activities which pertains to design and manufacture, they take a geometry as an input or they return the modified geometry based on certain feedback. So, when I am actually working in an environment like this, I can call it as a CAD CAM. So, the CAD CAM is something more than pure computer aided design or computer aided manufacturing. Now, this type of framework is also used in many CAD CAM systems. Like when you use a software, okay, let us say a CAD software or a CAM software or whatever it is, you may have a software which actually can do only one of these functions. Like there are number of finite element analysis packages which can do stress analysis, heat transfer analysis or CFD analysis or electromagnetic analysis, and the purpose of software is only to do analysis. So, it pertains to one aspect of a design. I may have a software which does only kinematic and dynamic analysis, okay, and nothing else, or I can have which helps only in terms of helping in a conceptual design, like I can use some innovation tools which are software based, which can help me in conceptual design process. We also know that there are software packages which can do only a CNC program generation, okay, nothing else. Similarly, you have software which specializes purely in assembly. Now, when you say CAD CAM, one approach is that you are putting together all these individual softwares and trying to integrate in some manner. That means, you have a links from one to go for another, and this kind of framework is designed by the person or an organization which is trying to use all these software packages. A second way of looking is that if I have a software which has all these modules, okay, like I buy a single software, that means under one umbrella I should be able to do all these activities, that is another approach. So, when you say CAD CAM systems, like usually you may have come across a term what is called as a high end CAD CAM systems. So, what one means by high end CAD CAM system is that a system which has like modules for all these activities, and you are able to do all these activities under a single software or under a single umbrella, but it is not necessary. If I prefer to go in terms of using individual softwares, I can always for example use the packages, but when I am using a separate packages, there is one thing which one has to do is that there is a geometric data has to be transferred from one system to another continuously. So, this is called as a geometric data exchange. Like this shows a geometric data exchange which has to be done. Like if I am using individual pieces of software, I have a geometric format in which, like I have a software 1 which stores geometry in certain format, then I have another software where this geometry has to be translated or transferred, then I have a second software where the geometric format is different. Now, whenever there is a change in a geometric format, a data transfer is necessary from one system to another. Now, this is necessary because like for example, if I want to store a geometric entity, there is no unique way it can be stored. Like if I take a simple example of a circular arc, okay, I think we discussed this some time back also, is suppose if somebody has to represent or store a circular arc, what should be the input? Okay. Somebody may say it should be stored by inputting, let us say, a center point of the arc, start point or end point, radius, start angle, end angle. You may not need all these values. Any combination or certain combination of this is enough to store a circular arc uniquely. So, a package 1 may store in some manner, a package 2 may store in some other manner. So, whenever there is this thing, I need to translate. So, the two arrows which you are seeing here are another pieces of software which are called as geometric data translators, which take a file from software 1 and transfer it to a format which can be read by another software, and you need a bidirectional translators in order to have an exchange from one particular system to another. Other way of looking at geometric data translation is, in order to move from, let us say, one particular system, one particular software to another particular software, I do not have a direct translator between these two packages, but I make use of some intermediate format which can be a standard or which can be you can say in a universally accepted format in some manner, and I can have a translator to convert it from, let us say, geometric format of software 1 to, let us say, this intermediate format, and then I can have another translator which goes from intermediate format to a geometric format. If I want to move it in the other direction, I have to follow the second set of translators which are available. So, this is another, you can say, another way of doing a translation process or transferring a geometric data from one system to another. Now, somebody may say which one should be, which one is like more preferable kind of a thing. Here I am using only a 2 translator, whereas here I have a 4 translator. This actually depends on various factors. Usually the direct translation is more reliable. Okay. Sometimes what happens is when I am going through an intermediate format, there may be some information which may be lost. Okay. So, somebody may say this is a more reliable option, but there is also advantage of this. Imagine I have for example, 7 different systems which have 7 different formats, and if I have to have a translators for converting from one to another, if I follow this approach, how many translators do I need? No, you need between any 2 combinations. For example, 1 to 2, 1 to 3, 1 to 4. So, you need basically a 7C2. Okay. 7C2 is the combination into 2 because it is a bidirectional translator, whereas here I have a 14 translators because you are going through intermediate and then doing this. So, the number of translator in that kind of a situation, this may be a more beneficial, whereas here if I am going for a bidirectional, then I need many more translators than. So, as the number of systems among which the data transfer increases, that means more the systems, the better would be this kind of a system. And this also has an advantage that you are making use of an intermediate format which is like more universally accepted. So, if I have to communicate, if there is a communication, if the data has to be transferred, let us say from one system to another system or one organization to another organization, there has to be some you can say an acceptable standard through which people can communicate. So, this is another way in which it has to be done, and the geometric data exchange is becoming more and more important as we discussed earlier, like a big organization would like to subcontract or buy major components from another this thing, but as a part of this you are actually trying to transfer the data. For example, if I take an example of an aircraft company. So, an aircraft company may buy engines from 3 different companies who are specialized or who specialize only in engine manufacturing. So, naturally you require the geometry which is related to geometric data related to engine if I want to carry out the assembly or virtual assembly operation when I am designing an aircraft. So, since I need a continuous data exchange, if I have some kind of an universally accepted format, many people can communicate. So, that is a major advantage of this process. So, with this objective in mind, there are number of geometric data translators which have evolved over a period of time. Like some of these translators are shown here, like you may have come across the term IGES. IGES is an ISO standard which is the one of the first standards which was designed or you can say developed for the geometric data exchange, and most of the CAD CAM systems, those systems which do pure computer aided design, pure computer aided manufacturing, give some kind of an interface with IGS. So, they give a translators to translate the data from and to from IGS. So, I can carry out this particular process. Then STL is another format. This is called as a stereolithography format, and this format is usually more common in rapid prototyping machines. So, in all rapid prototyping machine, I have to input is a CAD model. So, there are variety of CAD variety of rapid prototyping machines which are available in the market. So, what is the data? Like all of them they accept a stereolithography or a STL format, or most of them. Similarly, you have different nations have their own standards, like VDA is a German standard, SET is a standard which is used by French. Okay. So, there are national standards which are developed for geometric data transfer. DXF is a standard which is developed by one of the CAD packages, but is also quite popular for data exchange. Render is another format which is usually used for computer graphics application. Patron is also a standard which is very commonly used for many finite element applications and others. And VRML is again another format to define and translate the geometry, which is basically developed for web applications. Okay. Now, best way to understand the VRML, which actually stands for Virtual Reality Modeling Language, is all of you use World Wide Web for browsing and for interacting or for certain applications. So, you also come across images. Images are usually stored in either GIF format or JPEG. So, GIF and JPEG can give you only an image, which is a two-dimensional image. Suppose if somebody has kept a part model somewhere and I would like to basically click and rotate it, and I would like to see it from different views. So, I want a three-dimensional geometry in order to interact, then you can go for a VRML. So, what you do as a part of VRML is, suppose I create a part model and I convert into a VRML format using a translator which is available, and put it on the web and throw it open for others to use and interact. So, others can open. What they are basically looking at is not just a static image, but they are able to interact and walk through the part or part assemblies and get a better picture of this particular thing. So, VRML is mainly for the is primarily or more commonly used for the World Wide Web applications. So, these are some of the formats. Again, this is not a very comprehensive. There are many package to package translators which are developed, but some of the commonly used geometric data exchange formats are shown here. So, these geometric data exchange formats somewhere sit here, and then you have a translators from various packages, and that is how the data exchange happens. Now, we discussed that in a typical CAD/CAM environment, you have a more integrated approach, where various design and manufacturing activities continuously either use the geometry or update it, etc. Now, this particular slide basically gives that an environment like an integrated environment is very useful in order to reduce, let us say, product development time and cost. In any new product design and development process, okay, you never arrive at, let us say, a particular design in one step. It is a continuous process, an iterative process. The design undergoes change during conceptual design stage, during detailed design stage, during analysis, during manufacturing. So, there are various stages at which the geometry undergoes change, but it is also important that when the changes usually occur. For example, if I carry out any number of changes in my design during the design stage itself, it costs less, but once I have, let us say, finalized a design, now I am going for a functional testing. If I try to change a design, then it costs little more, you have to go back and do the design process. So, it has been tested, now it has you have a detailed drawing, detailed design of this, and you are going for manufacturing. The first step is a process planning. At the stage of process planning, you realize that there are problems with the design geometry, and you change it, you have a more cost which is associated. Process planning is ready, now you are actually going for a production, and if the design changes happen at that stage, it costs you even more, and during final production, or let us say it is in the market, and the actual you can say a problem with the geometry is coming from, let us say, as a feedback of customers, etc., then you have more cost implications. So, what basically the purpose of showing this particular picture is, one may have to account for all these things. That means, change of design during these stages may not be you cannot avoid them. One has to reduce as far as possible, and secondly, if these considerations can be brought down at the design stage itself, like when we say design for manufacture or design for assembly, some of these design changes which may happen, you are actually trying to do it here. So, if I go through a sequential process, then I have a problem. If I go through an integrated approach, where all these considerations are taken care at the design stage itself, then you have a benefit. So, the advantage of integration is evident from this, that you are considering these aspects, but at a design stage with a less cost implications, rather than doing them in a very sequential manner, first design next manufacturing, you have more cost implications which are here. So, that is the basic, you can say, benefit, major benefit of CAD CAM over individually CAD plus CAM which we are doing. Now, this kind of framework which we discussed, where geometry forms a basis for integration for integrating the design and manufacturing, was like basically developed in late 70s and early 80s. Okay. So, from early 80s itself you have a framework like this, which is already there as a part of packages, or you can say major high end CAD CAM packages, where geometry based integration is already there. But in recent years, particularly in last 2 decades, it has been realized that integration based on purely geometry is not enough. Okay. So, what is happening is the information which is exchanged between various activities is design, that is you can say a geometric information. So, geometric information is only one part of a design information. There may be a much more data or much more information which may be associated with a product. So, if you are doing purely a geometric data transfer and geometric data exchange, you have a benefit, you are working in an integrated manner, but you can go beyond geometry and do that. For example, we can look it from an example. Suppose I am trying to carry out a design process and I would like to know how much this part is going to cost me. It is not a very easy question to answer. Okay. I may have a very good integrated framework where there is a geometric data exchange happens, but still it is difficult to answer this question. The reason is, what constitutes, let us say, a cost of a product? There are many things. Okay. You have a material cost, you have a manufacturing cost, you have an inspection cost. There are various costs which put together will basically form the cost of this thing. Suppose I take at, let us say, one aspect of this, a manufacturing cost. So, naturally I have an integrated framework where I can go and let us say carry out, let us say, an NC program or this kind of a thing, and know what kind of manufacturing or how to manufacture this particular product. Now, when it comes to a manufacturing cost too, it is not very easy to do that, because if I am trying to find out the manufacturing cost, I should know various other costs, like what are the material cost, what are the tooling cost, which manufacturing machines will be used, okay. And if I am using a certain manufacturing machines and manufacturing process, whether they are available in my organization or not, or I have to buy it or I have to subcontract, all these decisions have to be taken in order to answer this particular question. And as a part of this, geometry alone cannot help. Just take an example. I know that this component is going to be manufactured by, let us say, a process like a die casting, or let us say a component has to be manufactured by machining. Now, you input a geometry because you have a very good framework for inputting and like exchanging the geometric data. I cannot decide the cost purely based on geometry. Maybe I need what kind of tolerances this particular part has, what kind of surface finish is required on this particular part, and the type of surface finish which is required will be decided by what is the functionality of a product, what is the intended function of the component. So, since you require more information than geometry, like I took an example of a tolerances or a surface finish, exchanging pure geometric information is of some help or of some benefit, but a better information exchange mechanism should take the complete product information into account. So, that is what has been a realization of last, you can say, 20 years, and now people are trying to bring again a framework for an integration where you have a CAD CAM, but the information exchange is beyond geometry, which includes the complete product information. So, this is usually called as a product modeling. Okay. Like this basically summarizes what I said just now. So, if I want a tighter integration of design and manufacturing, information exchange should go beyond geometry. So, I move from geometric model to what is called as a product model. In a product model, geometry is a subset, but it includes many other informations which are usually needed for taking certain decisions. So, a product modeling can be defined as basically information and exchange of related to all the life cycle activities. I think the word life cycle comes here. Life cycle is an important word to know. So far we have been discussing about design and manufacturing. When you say that there is a product, design and manufacturing are only a certain phases in a product life cycle. Now, a life cycle may include information which is beyond design and manufacture. Like once the manufacturing is over, you would like to bring, let us say, marketing information, or how to maintain this particular product. How the product should be maintained also requires product related information, and how the, let us say, product life is over, I want to dispose of the product. So, let us say whether it is possible to recycle this particular product or not, even that information is a part of a life cycle. So, life cycle is from the birth of a product till you dispose it of this particular product, all the information which is related or which is required, all the product information which is required is usually put as a part of a product modeling. So, exchange is possible not only between design and manufacturing, you can go for other activities too which are possible. So, the product modeling is, like you can say, product modeling based integration is now a focus in many of the CAD/CAM activities. Now, what information other than geometry is required? There can be many can say many different type of information which one may require as a part of a life cycle. Even if I look at design and manufacturing point of view, I have put a few of these. Okay, this is again not a complete list, this is only a sample information. Other than this, function, do I have, let us say, a framework where given a particular product, I am able to define what is the functionality of a product. Like you, when you store, let us say, a particular part, let us say if I take if you suppose somebody has a design for a connecting rod in a computer aided design package. So, you retrieve, you know that this is a connecting rod, or somebody may label it as a connecting rod, but the person who is trying to retrieve may not really know what is the intended function of a connecting rod or what this particular part is supposed to do. So, I should be able to store the functionality also. I should be able to store what are the specification and constraints. Like you may design a connecting rod for various applications, some may be for very high corrosive applications. So, you have a constraint that this is a connecting rod, this is a function of this, but it has to work under certain constraints, those can also be stored. And what are the specifications for which this has been designed? Geometry we have already discussed, with which we are familiar. Design history, the designer who tried to design this particular connecting rod has gone through a number of versions. So, what are all the versions? How did the design start? How the modifications were carried out, and why these modifications were carried out? You store the complete design history. Now, design history also helps one to know, suppose if I am going back for a redesign which has already been done in the past and there was some disadvantage, you do not have to repeat it. You can just retrieve the design history and know what is the problem in, let us say, changing the design in certain manner. Material information. Material information is so critical for all the design, manufacturing, recycling, maintenance, for all sorts of applications. Assembly and bill of materials, tolerances and surface finish, process data. Okay. You would also like to say that once the process plan for the component is generated, you would like to store that also, that this is the, you can say, the complete process plan for the component, or I may have some business information related to this particular thing. So, if if I can design a file just like an IGS file can store a geometry, but if I have a file which can store all this information and much more, then you say that you have a product model and I can have exchange which is possible based on the product model. Now, one of the solutions which is given for this is what is called as a step. IGS is an international standard, ISO standard. Similarly, step is another standard which has been developed to exchange the product information. Now, this is given basically step stands for standard for exchange of product data. ISO 10303 is the number for this. So, what is the purpose of step is it is an international effort. Many countries have come together to develop this particular standard, which basically consists of computer interpretable representation and exchange of product data. It is not geometric data. Geometry is included as a part of a step, but it has other information which is related to product, which we have looked at this. Now, just to give an example, suppose I design a product in one of the packages and I assemble it. So, I have assembly information. Assembly information includes what are the components which have been put together and what are the mating relationships. Now, if I want to take this assembly to another CAD/CAM package, suppose if I have a translator, geometric data translator like IGS, it is not possible to do that. What you have to do is, I can take the individual geometries of the components to another package and do the assembly there, because IGS will not give you a provision to also store the mating relationship. Now, suppose if I have a step file, a step has a provision to store the assembly information also. So, once I prepare an assembly of the product, I generate a step file, take the step file in another package and open it, you can also see that the assembly information is preserved, all the mating relationships are preserved. So, it is like an example of going beyond geometry, and it is possible to do that. Most of the CAD/CAM systems now, they also give step as a translators. In fact, IGS and step are the two common which you will find with most of the CAD/CAM packages which are available in the market. I can always create a step file. I can use step purely for geometry purpose also, but I can suppose the component has been given certain tolerances and I want that these tolerance information also be exchanged between packages. It is possible to do using a system like a step. Now, another important concept. So, the basic summary which I wanted to do is that if I go for, let us say, a design and manufacturing integration framework which is more like step based, then you have further advantages. That means more decisions can be taken quickly, and it also has lot of cost implications. Another way a product data can be managed and exchanged is what is called as a PDM, or product data management software. What basically product data management consists of is it has a server which is basically a computing system which is used to exchange information between various departments. Then it also has a database where the information is stored, and if there are many, you can say, departments in an organizations, and all of them, they are concerned with the same product. Somebody is designing, somebody is manufacturing, somebody is inspecting, somebody is preparing a process plan for that. So, and this design is continuously undergoing a change. So, how do I tell others that the design has changed? Is if the design can be stored centrally in a server, and if everybody refers to the same design, then you have a framework which can be used to communicate. For example, somebody has started with design and come up with a first version of a design and posted it on a PDM server. So, the moment somebody posts or somebody says that a design has been added to PDM server also sends information either through email or this thing that a design for this is now available on this. So, other departments who are concerned with that particular product can look at that design and see. For example, a process planner can generate a process plan and see that there is a problem. So, there is a problem if you modify the geometry in, let us say, this manner, process planning would be much more optimum. So, process planner will modify the geometry and post it on a PDM server, which is again broadcast to all the other departments. So, designer can again go back and see whether the geometry which has been modified by a process planner, does it still meets the functional requirements, because designer is more concerned whether it will do the intended function satisfactorily or not. Since a product information is critical to many people, so if everybody is modifying, then they can always post it or they can put it at a central place. So, this will have a various versions. Suppose if the design has undergone, let us say 10 times a change from version 1, 2, 3, all the designs are stored. If somebody wants to refer why this has happened and how it has happened, one can always take back. So, and PDM can store information in various ways. It can be a text file, it can be an image, or it can be an IGS file, or it can be a step file, or it can be CL data, that is cutter location data which has been generated as a part of a program. So, all the information which pertains to product, you put it on a central place which facilitates people to exchange the information quickly. Otherwise, suppose if I do not have such a framework, somebody carries out a design, then you send the information to all the departments. So, you are, and the person may receive, let us say you send it as a post or a as a drawing, then somebody may look at and take some time to feedback. Information is not instant whenever there is an update or this thing. So, there are always delays which can be and also since you are sure that most of the people who are working with the same product, they are not working with different versions of a design, okay, because the most latest version of the design is available is told by what the PDM server has. So, this kind of software is also nowadays becoming very common. In fact, many of the organization in India and abroad, major organizations, they use this kind of framework, and there are at least half a dozen very popular PDM softwares which are available in the market. So, when I buy a CAD/CAM packages, I also buy a PDM software, so that I will have this kind of thing. For example, if I am using a package and I want to store my design in a format which is specific to that package, I can also put a file related to this. So, PDM server need not have the formats which are only ISO standards or this thing. So, it can be anything which can be used either in the form of data or in the form of this thing, but it is usually a digital data, that means you have information in a digital kind of a thing. So, a format like STEP together with like an information like PDM facilitates a fast exchange of information among various departments, and is such a framework is used to reduce the basically the product design and development time, and also it has a cost implications. Okay. So, that is basically I would say that a summary of this particular lecture. What we try to do is that instead of using computers purely for a design and manufacturing point of view, you are working in a more integrated fashion, either by exchanging the geometric information or by exchanging the product information, and this exchange of information could be through a framework like product data management system which are available. So, usually what happens is if somebody has to implement such a framework, in fact, it is very common that an organization has 10 different branches in the country or across the globe, and there is one particular you can say branch which actually designs, whereas the other branch takes care of the manufacture, which are thousands of miles away, but everybody works with the same PDM system. Like there is a central PDM server which is serving all the, let us say 10 or 15 branches of the company. So, as and when let us say a particular the geometry or product information undergoes a change, you post it and people can communicate kind of this particular thing. Like for example, Indian Railways uses a product data management system for exchange of this kind of information. So, there are many such examples in India and abroad where people use CAD/CAM systems together with a PDM for you can say for major benefits which can be achieved. Okay. So, I will just stop it here, maybe I can take up a few questions. So, during this particular lecture, if you have any doubts, so then you can clarify, or you want to add anything to this, can also.
Can you give any example of PDM software?
So, the question is, are there any examples of PDM software? Yeah, for example, there is a PDM software by the name Windchill, then you have a PDM software by the name Metaphase, then you have a PDM software by the name iMan. In fact, these are all different PDM software is basically used by, also developed by different people who develop the CAD CAM systems. Sometimes like you also have a very good compatibility between a specific CAD CAM package and a specific PDM software, because they have been developed by the same company or same software company. So, these are all available in the market which people use, kind of a thing. Or I can have my own in-house framework for a PDM. It's not difficult to do, because only thing is PDM software gives you is the communication aspect is very well taken. Otherwise, you have to have all the modalities for communication, and if suppose somebody is going to post a design, what would be the format, everything has to be designed. Otherwise, it is more or less pre-decided in a PDM kind of a framework. So, these are some of the examples. Any other question? Okay. If there are no questions, so what we basically had as a part of these 3 lectures is to look at computer aided design separately, computer aided manufacturing separately, and an integrated framework for CAD CAM, what we covered today. Now, based on these 3, you can say introductory lectures, now we will look at some of the individual CAD CAM applications as a part of our subsequent lectures, and also more so keeping this framework in mind. Okay, that is more important. Like one can always study, there are books on CAD CAM, and there are also curriculum in CAD CAM where these functions are separately studied, but without this integrated framework in mind. And it is very important, particularly if you look at the way industry operates now and the way they are moving, this integrated framework is becoming more and more common. So, we will study the individual functions and also this framework, but always keep that we are looking at CAD CAM, not at computer aided design or manufacturing, which are separately. So, I will just stop it here.